In today's video we will explore about what is network congestion. Network congestion occurs when the number of transactions submitted to the network exceeds its capacity to process these transactions. This phenomenon has several contributing factors, such as external factors including market volatility and intrinsic network characteristics such as block size and block time. How does blockchain technology work? A blockchain consists of a chain of blocks, each block containing transaction data created by users. Each new block that is added to the chain is permanent and immutable. These blocks are propagated across a decentralized network of nodes, each storing a copy of the blockchain. Secured by cryptography and game theory, blockchain forms the backbone of cryptocurrencies like Bitcoin and Ethereum. To fully understand why blockchain networks can get congested, we'll need to explore the key concepts that play a part in a network's ability to process transactions. What is a mempool? A mempool refers to the collection of unconfirmed transactions waiting to be included in the next block. For example, when a transaction is broadcasted on the Bitcoin network, it doesn't get added to the blockchain immediately. Instead, it first goes into the mempool, short for memory pool, which is essentially a waiting area for all pending transactions. A transaction will be removed from the mempool once it's been confirmed. What are candidate blocks? Candidate blocks, also known as proposed blocks, are the ones miners or validators propose to be added to the blockchain. These blocks contain unconfirmed transactions that have been broadcasted to the network but haven't been included in the blockchain. For a candidate block to become a confirmed block, it must be mined or validated according to the blockchain's consensus mechanism. For instance, Bitcoin's proof of work (POW) consensus mechanism lets miners compete to solve a complex mathematical puzzle. The first miner to solve the puzzle gets to add their candidate block to the blockchain and earn a reward. What is finality in blockchain? Finality is when a transaction or operation can no longer be changed or reversed. Once a transaction has achieved finality, it's permanently recorded on the blockchain and can't be altered or removed. In the Bitcoin blockchain, transactions are broadcasted to the network and added to the mempool. Miners select and verify transactions from this pool and include them in new blocks to be added to the blockchain. The transactions included in that block are considered confirmed, but it's theoretically still possible for other miners to mine a competing block. The finality of transactions increases with the number of confirmed blocks. Bitcoin transactions are typically regarded as final once an additional 6 blocks have been appended to the block that contains these transactions. Due to Ethereum's shorter block time, a larger number of confirmations are recommended to achieve a similar level of confidence in finality. What is the longest chain principle? As illustrated above, multiple miners can produce new valid blocks at similar times. This can result in temporary forks in the blockchain. The longest chain principle refers to the rule that the valid version of the blockchain is the one that has the most computational work invested into it, which is typically the one with the longest chain of blocks. As a result, the valid blocks on the shorter chains, often called orphan or stale blocks, are discarded, and their transactions get returned to the mempool. Ethereum used the longest chain principle when the network used proof of work (POW). After Ethereum's transition to proof of stake (POS) in 2022, the network adopted an updated fork choice algorithm that measures the weight of the chain, which is the accumulated sum of validator votes weighted by validator staked ether balances. What causes blockchain network congestion? 1. Increased demand. As more people submit transactions to the blockchain, the number of unconfirmed transactions in the mempool can exceed what can be included in a single block. This is particularly relevant for blockchains with inherent limitations in block size and block time. Increased transactions can be driven by sudden price volatilities leading to a surge in transaction activities or waves of mass adoption cycles. 2. Small block size. Each blockchain has a block size that defines the maximum size a block can be. This block size limits how many transactions a block can include. For example, Bitcoin was initially designed to have a block size limit of 1 megabyte. In 2017, Bitcoin implemented an upgrade called segregated witness, or SegWit, to improve transaction throughput. It increases the theoretical block size limit up to approximately 4 megabytes. If the number of transactions exceeds this limit, it results in network congestion. 3. Slow block times. Block time refers to how often a new block is added to the blockchain. Bitcoin adds a new block about every 10 minutes. If transactions are being created at a much faster rate and volume, there will be a backlog of transactions. What are the consequences of network congestion? 1. Increased transaction fees. Miners are incentivized to prioritize transactions paying higher fees. So when a blockchain network becomes congested, users often need to pay higher transaction fees to incentivize miners to prioritize their transactions. This can make using the blockchain more expensive than usual, particularly for smaller transactions. 2. Delayed transaction confirmation times. Network congestion can lead to longer waiting times for transaction confirmations and finality. In extreme cases, transactions may not be confirmed for several hours, days, or even longer. This could cause frustration for users. 3. Poor user experience. High fees and slow confirmation times can result in a poor user experience, which could potentially reduce the adoption and usability of the blockchain. 4. Market volatility. Congestion could amplify uncertainty and contribute to market volatility. If there are many users trying to sell a cryptocurrency, but the network is too congested to process these transactions, users could panic. There are other consequences, including security risks and network centralization risks. Specifically, longer confirmation times can increase the risk of double spending attacks, and high fees could lead to the centralization of mining power. Examples of network congestion. Both the Bitcoin and Ethereum networks have experienced significant network congestion. 1. Bitcoin network congestion. Bitcoin's notable price increase between the end of 2017 and early 2018 led to one of the most prominent network congestion events to date. The surge in Bitcoin's popularity led to a massive increase in demand and transactions, resulting in significant delays and eye-watering transaction fee increases. At one point, average transaction fees were over $50. In the spring of 2023, the Bitcoin network became congested as increased transaction activities related to BRC-20 tokens caused pending transactions and fees to skyrocket. At one point, nearly 400,000 unconfirmed transactions were recorded, causing a bottleneck in the mempool. Transaction fees increased by over 300% within a couple of weeks. 2. Ethereum network congestion. One notable example of Ethereum network congestion occurred in 2017 when the CryptoKitties project went viral and significantly slowed down the network. There has also been network congestion due to the DeFi boom, resulting in increases in gas prices. Any blockchain network can become congested. But instances of network congestion on the Bitcoin and Ethereum networks have attracted more attention than that of other blockchains. Solutions to alleviate network. 1. Increasing block size. Increasing the block size allows more transactions to be processed per block, effectively increasing the network's throughput. But larger blocks take longer to propagate through the network, increasing the risk of temporary forks. They also require more storage space, which could lead to increased centralization. 2. Decreasing block time. Reducing block time can allow the network to process transactions faster. However, shorter block times can increase the number of orphaned blocks and potentially compromise security. While blockchain network congestion poses significant challenges, the community continues to develop solutions to help mitigate these issues. This is why research around blockchain scalability enhancement is at the forefront of the industry. Thanks for watching.